In the harshest environments on Earth, survival is defined by the control of heat. An absolute rule of physics: to overheat is to perish. But in the heart of the heat, millions of tiny architects have built a fortress. Witness the biological skyscraper, the termite mound, a masterclass in passive engineering. The colony requires a constant temperature of 31 degrees. To achieve this, the mound functions as a high-capacity thermal capacitor, managing extreme external fluctuations through precise architectural mass. Break the system down. Analyze the porous outer shell, a multi-layered biological composite designed for structural integrity and high-fidelity thermal shielding. Module 1, the thermal barrier, a massive outer shell with engineered thermal mass. It absorbs solar radiation during the day and releases it at night, managing heat transfer through passive phase shifting. The external barrier is established, but inside, a greater engineering challenge remains: the management of internal heat. Millions of organisms living in a single core generate massive metabolic heat. In a closed system, this energy is lethal. Look at the internal architecture. Break the system down. Module 2, the thermal chimney. Module 2, passive convection. Hot air from the colony rises through a central shaft, driven by the laws of thermodynamics. Constant exhaust. External winds create a low-pressure zone at the top, drawing the hot, stale air out of the system, a biological vacuum. Working together, these features achieve one goal: a self-regulating atmosphere that never sleeps. Precision through physics. Every living core needs to breathe. The termite mound is more than a shelter. It is a biological lung. Deep within the skyscraper, millions of organisms consume oxygen and release waste gases. A buildup of CO2 is the silent threat. Look at the respiratory architecture. Break the system down. Module 3, atmospheric exchange. Module 3, porous diffusion. The walls are not solid, they are a semi-permeable membrane that allows gases to pass while keeping the heat out. Fluctuations in external wind pressure drive the exchange. CO2 diffuses out, fresh oxygen filters in, a passive respiratory cycle. Working together, these structures achieve one goal: total atmospheric homeostasis, life sustained through architectural breath. The engineering is proven, but can a biological system from the savanna redefine the modern city? By mimicking the thermal mass and chimney effects of the termite mound, architects have unlocked a new path for sustainable design. Scaling the design, the Eastgate Center in Zimbabwe, a massive concrete skyscraper that breathes without a traditional air conditioning system. The result, 90% less energy consumed, a building that manages its own internal climate through passive thermodynamics. A biological system scaled to human proportions, working together to achieve one goal: efficiency through design. We have analyzed the mass, the ventilation, the architecture. Now we look at the future of our own species. Nature's passive cooling is more than a survival trick. It is a blueprint for zero-energy urban environments. By scaling these biological systems, we can combat rising global temperatures through architectural intelligence alone. Engineering for a changing planet. Scaling the design. From the parched earth of the savanna to the smart breathing infrastructures of our future civilization. A biological system where every pore and tunnel contributes to one goal: efficiency through design. Working together. This is not just an insect nest, it is an ancient masterclass in sustainable engineering, a legacy for our future. At Design by Nature, we don't just see nature, we see the future. Analysis complete. The file is closed. I'll see you in the next analysis.